Your middle schooler walks in and announces they need to collect pollution data for a science fair project. You're picturing construction paper and pie charts, but what if they could deploy actual monitoring equipment, contribute to real research databases scientists use, and build the same data skills environmental engineers rely on every day? I'm Lakshmi Venkataraman, a national board-certified middle school science educator with a master's in curriculum and instruction. I've watched this exact transformation happen dozens of times in my classroom, and it starts with choosing the right monitoring equipment.
You're listening to the STEM Lab podcast. Quick heads up before we get going. Everything you're hearing today, all the research, the recommendations, the teaching insights, that's all human created and verified by real educators. The voice you're hearing, though, that's AI generated, which lets us get these episodes to you consistently and efficiently. I'm really grateful to those of you who've been listening for a while now. You make this worth doing. And if you're just finding the show, welcome aboard. New episodes drop every Monday, Wednesday, and Friday, so there's always something fresh coming down the pipeline. Now, let's get into what we've got for you today. The best environmental monitoring kits for kids balance accessible entry points with genuine scientific rigor, offer compatibility with both block-based and text-based programming, and connect young researchers to authentic citizen science networks where their data actually matters. Now, let's talk about what you should actually look for when you're choosing one of these kits. The most effective environmental monitoring kits bridge the gap between visual programming and industry standard tools. Look for systems that support multiple programming environments, typically starting with block-based interfaces like Scratch or MakeCode and progressing to Python or Arduino IDE. This scaffolds beautifully. Your 8-year-old can begin with drag-and-drop sensor blocks, while your 13-year-old uses the same hardware to write Python scripts for data analysis. OS requirements matter more than you'd expect. Many kits claim they work with any device, but require specific browser versions, Bluetooth LE support, or desktop software that won't run on older Chromebooks or tablets. Verify whether the kit requires constant cloud connectivity or can log data offline. That's critical for field deployment where Wi-Fi isn't available. I've watched too many promising investigations stall because a kit needed real-time cloud sync during a park deployment. Check whether the platform uses open-source libraries or proprietary software. Open-source systems, like Arduino-compatible boards, mean your child can transition directly to tools used in university research labs and environmental consulting firms. Proprietary ecosystems often hit capability ceilings right when students are ready for more sophisticated analysis, forcing you to start over with entirely new hardware. Moving on to sensor accuracy and calibration. Here's where many educational kits disappoint. They measure something, but the data isn't accurate enough to teach proper scientific methodology. Professional-grade environmental sensors require regular calibration, and that's actually a valuable learning opportunity if the kit supports it. It's a deal-breaker if it doesn't. Look for kits that specify sensor resolution and accuracy ranges. A temperature sensor accurate to plus or minus 2 degrees Celsius teaches fundamentally different lessons than one accurate to plus or minus 0.3. The first might show daily trends. The second can detect microclimate variations that actually matter for ecological studies. For air quality sensors, check whether they measure particulate matter like PM 2.5 and PM 10, volatile organic compounds, or just proxy indicators like humidity. Calibration workflows separate serious citizen science tools from toys. The best kits include calibration protocols using reference standards, even if that's something simple like placing the sensor in a sealed bag with a humidity packet for humidity sensors. This teaches essential sensor calibration skills and helps students understand measurement uncertainty, a concept that bridges directly to next-generation science standards on data reliability and experimental design. Consider whether the kit connects to established citizen science databases like EPA's Air Sensor Toolbox or community networks. When your child's data contributes to actual research, when they can see their readings on regional air quality maps alongside professional monitoring stations, the learning shifts from abstract to deeply meaningful. Now let's discuss expandability and modularity. The most valuable environmental monitoring kits function as platform investments, not one-off projects. Look for systems with standardized expansion ports like I2C, Grove connectors, or Qweek interfaces that accept additional sensors without requiring soldering or advanced electronic skills. A strong learning pathway might start with a basic temperature and humidity kit at age 10, add soil, moisture, and pH sensors for a gardening project at 12, then integrate GPS and SD card logging for watershed mapping at 14. This progressive complexity builds data collection and analysis capabilities that compound over time rather than starting fresh with disconnected tools. Modularity also means failure resilience. When, not if, your child drops a sensor in a creek or accidentally reverse polarizes a connection, can you replace just that component, or does the entire kit become e-waste? The best designs use interchangeable sensor modules with clear troubleshooting documentation, teaching debugging skills alongside environmental science. Check whether the ecosystem supports third-party sensor integration. Can you add a professional-grade CO2 sensor from a lab supplier once your child masters the basics? Systems that work with industry-standard protocols like I2C or OneWire future-proof your investment and prepare students for actual field research equipment. Let's move on to power management and field readiness. Classroom demonstrations and backyard monitoring have vastly different power requirements. If your goal includes multi-day field deployments, tracking stream temperature across a weekend, or logging air quality during a local event, you need realistic battery life specifications and weather resistance. Many kits advertise portable designs, but realistically run for 4 to 6 hours on a USB battery pack. That's fine for a school day, inadequate for overnight monitoring. Look for systems that support low-power sleep modes, log data locally, not just stream it, and can run for 24-plus hours on rechargeable battery packs. Solar charging integration is a bonus that ties directly to renewable energy concepts. Weatherproofing requirements vary by deployment scenario. An enclosed case with IP54 rating handles light rain and dust. Serious outdoor monitoring needs IP67 protection for sensors, which means submersible. Some kits cleverly separate the sensor heads, which can be weatherproofed, from the main electronics, which stay dry. That's a design that mirrors professional weather stations and teaches practical engineering constraints. Consider data logging capacity and retrieval methods. Does the kit require you to connect a laptop in the field to download data, or does it log to a micro SD card you can swap out? Can it transmit data via cellular, LoRa, or Wi-Fi for remote monitoring? These aren't just conveniences, they're fundamental decisions about study design that students need to understand before deploying equipment. Now, documentation and community support. The best environmental monitoring kits include structured learning pathways, not just technical manuals. Look for guides that scaffold investigation design, how to formulate testable questions, design data collection protocols, analyze patterns, and communicate findings. This pedagogical structure matters enormously for home learners who don't have classroom support. Strong online communities transform isolated tinkering into collaborative science. Check whether the kit connects to active forums, Discord servers, or classroom networks where students can share methodologies, troubleshoot problems, and compare data sets across different geographic regions. I've watched students far more motivated by seeing their air quality data compared with a peer group across 3 states than by any grades I could assign. Integration with existing curriculum frameworks reduces your planning burden. Kits aligned with NGSS standards, particularly the ones focused on human impacts on environment and Earth systems, include investigation templates, assessment rubrics, and connections to broader environmental science concepts. Some explicitly prepare students for science fair formats or Research Science Institute applications, valuable context for high schoolers building research portfolios. Look for transparent upgrade paths in the documentation. Does the manufacturer clearly articulate how this kit connects to more advanced tools? The best companies show explicit progression. Start with this all-in-one kit at age 10 to 12, migrate to modular sensors with Arduino at 13 to 15, then transition to Raspberry Pi with professional sensor libraries for high school research projects. That roadmap is pedagogical gold. All right, let's get into our top picks. First up, the Microbit Smart Citizen Kit. Check the link below to see the current price. This combines the widely adopted Microbit platform with environmental sensors specifically calibrated for community air quality monitoring. This kit scaffolds beautifully from block-based programming and MakeCode to JavaScript and Python, using the same hardware throughout, exactly what you want for progressive skill development. Here's what works really well. You get dual programming interfaces, MakeCode blocks for ages 8 to 11, Python for ages 12 and up, using the same hardware. The pre-calibrated BME688 sensor measures temperature, humidity, pressure, and air quality, specifically volatile organic compounds, with documented accuracy ranges. The built-in LED matrix and radio enable students to build wireless sensor networks comparing data across multiple locations. It has offline data logging to onboard storage, plus optional cloud sync through the Smart Citizen platform that maps student data alongside professional monitoring stations. There are extensive curriculum resources aligned with NGSS standards. The power consumption is low, more than 20 hours of continuous logging on 3 AAA batteries, or indefinite operation with micro USB power, and there's a robust community. Thousands of schools worldwide using identical hardware, making troubleshooting and project sharing straightforward. The limitations worth knowing about: the expandability is limited. The Microbit Edge connector supports additional sensors but requires adapters that younger students find fiddly. The display size is constrained. That 5x5 LED matrix shows limited data visualization, so students need separate devices for detailed graphs. And the BME688 VOC readings are relative, not absolute. It teaches important lessons about sensor limitations, but you can't directly compare to EPA air quality standards without a calibration reference. Next, the Arduino Environmental Science Bundle. Check the link below for current pricing. This represents the gold standard pathway toward industry-standard tools. Built around the Arduino Uno R3, this kit includes DHT22 temperature and humidity sensors, GP2Y1010AU0F dust sensors for particulate matter, and MQ135 air quality sensors, all with open-source libraries that professional researchers actually use. Here's why this one stands out. It's an industry-standard platform. Arduino IDE and C++ programming are precisely what environmental engineering firms use for custom sensor deployments. You get true modularity. Standard pin headers mean students can add any Arduino-compatible sensor, and there are thousands available, without manufacturer lock-in. The sensor documentation is superior. Detailed data sheets teach how to read specifications, understand calibration curves, and calculate measurement uncertainty. An SD card logging shield is included. Students design their own CSV file structures and data collection intervals, which is crucial database literacy. There's no cloud dependency. Entirely offline operation teaches data sovereignty and works in field locations without connectivity. The long-term viability is excellent. Arduino skills transfer directly to college engineering labs, research internships, and maker communities. And the expandability is cost-effective. Replacement sensors typically cost $3 to $15, making experimentation and failure less stressful. The trade-offs here. There's a steeper initial learning curve. This requires understanding of circuit assembly, polarity, and basic electronics, not ideal before age 11 or 12. It's text-based programming only, no block-based option, making this inappropriate for students who haven't yet mastered the transition from block to text coding. And weatherproofing requires DIY solutions. The kit provides sensors and electronics, but students must design their own protective enclosures. That's a valuable engineering challenge, but time-intensive. Moving on to the Vernier Go Direct air quality sensor. Check the link below to see the current price. This brings professional-grade accuracy to student investigations. Vernier is the lab equipment company that middle and high school science departments actually use, making this a direct introduction to tools your child will encounter in formal STEM education.
The strong points here. You get research-grade calibration. It measures particulate matter PM2.5, temperature, humidity, and barometric pressure with accuracy comparable to EPA reference monitors. There's dual connectivity, Bluetooth wireless for field deployment with a 100-meter range, or USB for continuous monitoring with real-time graphing. Cross-platform compatibility is excellent. Works with Chromebooks, iPads, Windows, Mac via the Graphical Analysis app, which is free. The integrated rechargeable battery gives you 14+ hours of continuous operation with USB-C charging. Professional data export generates CSV files compatible with Excel, Google Sheets, and statistical software like R. Curriculum integration is built in. Vernier provides investigation manuals explicitly aligned with AP Environmental Science and NGSS standards, and the sensor lifespan and support are solid. It's designed for 5+ years of classroom use with responsive technical support and repair options. What to be aware of? It's a proprietary ecosystem. While data exports are standard formats, sensor calibration and configuration require Vernier's software. Programming access is limited. It's designed for data collection rather than learning to code sensor interactions. Students use Vernier's apps. They don't write their own. There's a higher price point. Professional calibration and build quality come at premium pricing versus DIY kits, typically around $200 to $250. And there's no expandability. This is a purpose-built instrument rather than a platform for adding additional sensor types. Next, we have the Raspberry Pi Environmental Monitoring Hat. Check the link below for pricing. This transforms a Raspberry Pi into a weather station and air quality monitor with sensors that detect temperature, humidity, pressure, light, particulate matter, and oxidizing and reducing gases. This represents the progression point for students who've mastered Arduino or microbit and are ready for Linux-based data science workflows.
Here's what makes this powerful. You get a full Linux environment. Students learn command line operation, Python scripting, cron jobs, and database management. Those are skills that define modern data science. Superior processing power means on-device data visualization with Matplotlib, statistical analysis with Pandas, even basic machine learning with scikit-learn. Network capabilities are built in. Wi-Fi and Ethernet enable remote monitoring, automated data uploads, and web-based dashboards students build themselves. Camera integration is possible. Add a Pi camera module for time-lapse documentation of environmental conditions alongside sensor data. This prepares you for professional workflows. This setup mirrors actual IoT environmental monitoring systems deployed by municipalities and research institutions. Multiple programming languages are supported. Python is most common, but also Node.js, Java, even R for statistical analysis, all supported natively. And long-term logging is handled easily. Micro SD card storage handles months of high-frequency sensor data without external downloads. The considerations here. This requires an existing Raspberry Pi. The hat, that's hardware attached on top, is an add-on board, necessitating separate purchase of Raspberry Pi 4 or Pi 5, around $50 to $80. There's a Linux learning curve. Students need comfort with terminal commands and file systems before this becomes accessible. Power requirements are higher. Raspberry Pi demands stable 5-volt 3-amp power. You can't run it on simple battery packs like simpler kits, limiting true portable deployment. And there's no pre-built software. Maximum flexibility means students must write all data collection and analysis code themselves. That's excellent for learning, time-intensive for quick projects. Then there's the Kestrel Drop D3 Environmental Data Logger. Check the link below to see the current price. This offers a different approach, professional monitoring equipment specifically designed for student access. Kestrel manufactures the handheld weather meters that wildland firefighters, military units, and research meteorologists depend on. This is their educational entry point. The advantages are clear. No programming is required. It's a sealed, weatherproof unit that logs data autonomously for 30-plus days on a coin cell battery. True field deployment is possible. IP67 waterproof rating means students can leave this in streams, hang it from trees, or deploy during storms without equipment anxiety. Bluetooth data retrieval is built in. The free Kestrel Link app for iOS and Android downloads data wirelessly through the sealed case. You get professional accuracy, NIST traceable calibration on temperature plus or minus half a degree Celsius, humidity plus or minus 2% relative humidity, and pressure sensors. Multiple deployment modes work with magnetic mount, carabiner clip, or direct stake mounting for diverse installation scenarios. Long-term data sets are possible. 10,000-plus data point storage enables semester-long investigations. And it's zero maintenance. The sealed design prevents sensor contamination and moisture damage that plague open sensor boards. The limitations to know. Sensors are limited, measures only temperature, humidity, and pressure. No air quality, light, or soil sensors. There's no programming learning. It's excellent for pure environmental science investigations, but teaches zero coding or electronic skills. It's a closed system. No expandability, no sensor swacking, no customization beyond logging intervals. And data analysis happens elsewhere. Students must export CSV files to other software for graphing and statistical analysis. That's good workflow practice, but it adds steps. Finally, the SparkFun Environmental Combo Board. Check the link below for current pricing. This packs CCS 811 air quality, BME 280 environmental, and VEML 6075 UV sensors onto a single, quick, compatible board. SparkFun's distinctive red PCBs are ubiquitous in makerspaces and university engineering labs, making this a genuine introduction to tools your child will encounter in advanced STEM spaces. What works really well here? The quick connector system means tool-free sensor connections using standardized I2C cables. No soldering, no breadboards, no wire confusion. Triple sensor integration gives you VOCs, CO2 equivalent, temperature, humidity, pressure, and UV index from one compact board. Arduino and Python libraries are available, well-documented open-source code for both platforms with example sketches for common data collection scenarios. Excellent learning documentation is a Spark Fun strength. Their tutorials explain not just how to use sensors, but why certain configurations matter and what the readings actually mean. The expandable ecosystem lets you daisy chain dozens of Spark Fun and third-party sensors using quick cables without electronic complexity. The small form factor, 1-inch by 1-inch board, fits in compact weatherproof enclosures students can design and 3D print. And there's an active troubleshooting community. SparkFun forums and GitHub issues provide responsive support when things go wrong. What you should know up front. This requires a separate microcontroller. It's a sensor board only, needs Arduino, ESP32, or Raspberry Pi to operate. That adds $15 to $40 to total cost. The CCS811 requires a burn-in period. The air quality sensor needs 48-hour continuous operation before stable readings. That's an important methodology lesson, but it delays immediate use. No weatherproof housing is included. Students must design protective cases, great for engineering practice, an obstacle for immediate deployment. And I2C address conflicts are possible. When daisy chaining multiple sensors, some share addresses requiring manual configuration. That's advanced troubleshooting that frustrates younger students. Now let's tackle some frequently asked questions. What age should kids start using environmental monitoring kits? Most children develop the patience and data literacy needed for meaningful environmental monitoring around age 9 to 10, when they can sustain multi-day investigations and understand that data collection requires consistency. However, the specific kit matters enormously. A microbit-based system with block programming works well from age 8 to 9 because the visual interface makes sensor readings immediately concrete. Arduino-based systems generally require age 11 to 12 minimum, when students can handle text-based coding and circuit assembly without constant adult intervention. The critical factor isn't just age, but prior skill development. If your child has worked through screen-free coding experiences and understands basic programming logic, they'll engage with sensor kits 1 to 2 years earlier than peers coming in cold. Similarly, students who've completed basic robotics projects already understand the sensor-processor-output loop that environmental monitoring requires. Focus less on arbitrary age gates and more on whether your child can articulate what they want to measure and why. That question formulation skill predicts success better than birth year. Do environmental monitoring kits require subscriptions or ongoing costs? Most hardware-based environmental monitoring kits require no subscriptions, but cloud platforms and some smartphone-connected systems do charge for data storage, advanced visualization, or access to community networks after initial trial periods. The Arduino Environmental Science Bundle, SparkFun boards, and basic microbit systems operate entirely offline with zero recurring costs. You own the hardware, and all data stays local unless you explicitly upload it. Vernier's Go Direct sensors use free software with no subscription tiers. Kestrel's Link app is free permanently. However, some citizen science platforms like Smart Citizen charge around $3 to $5 monthly for cloud storage beyond basic tiers, and advanced features like automated alerts or API access to historical data may sit behind paywalls. The hidden recurring cost is often sensor calibration and replacement. Air quality sensors, especially electrochemical gas sensors, degrade over 12 to 24 months and need replacement, typically $15 to $40 depending on sensor type. Particulate matter sensors can accumulate dust that affects accuracy, requiring replacement or professional cleaning. Budget around $20 to $50 annually for sensor maintenance if you're conducting serious, ongoing monitoring. This isn't a subscription, but it's worth factoring into total cost of ownership. The valuable teaching moment here is that professional environmental monitoring stations face these same maintenance requirements, so learning to track sensor health and schedule replacements builds authentic research skills. Can kids contribute real data to citizen science projects with these kits? Absolutely yes, and this is where environmental monitoring transforms from isolated learning exercise into genuine scientific participation. Citizen science networks like Purple Air, Globe Observer, and regional watershed monitoring programs actively seek student-contributed data, provided it meets quality standards. The key qualifier is sensor calibration and documentation. Research networks need to know what equipment collected the data, calibration status, and deployment conditions. Kits with NIST traceable calibration, like vernier sensors, or those that can be co-located with reference monitors for validation, like Purple Air compatible PM sensors, produce data scientists can actually use. Uncalibrated educational sensors teach valuable methodology but won't contribute to professional databases. I've guided students through successful data submissions to local water quality consortiums and air quality networks. The process teaches research rigor, maintaining calibration logs, documenting sensor placement with GPS coordinates, noting environmental conditions that might affect readings, and understanding data quality flags. When students see their weather station data appear on NOAA's Community Collaborative Rain, Hail, and Snow Network, or their air quality readings integrated into regional maps, the learning motivation jumps dramatically. Start by identifying which citizen science projects operate in your region, then choose monitoring equipment that matches their data collection protocols. That backward design ensures your child's work contributes meaningfully. How do environmental monitoring kits connect to STEM career preparation? Environmental monitoring kits build a remarkable skill stack that transfers directly to professional STEM pathways. Environmental engineering, atmospheric science, ecology, public health, climate research, and increasingly data science and IoT development. The technical competencies, sensor calibration, data logging, statistical analysis, spatial mapping, are precisely what environmental consultants, field researchers, and sustainability analysts do daily. More specifically, students who progress through environmental monitoring develop three career-critical capabilities. First, they learn to design data collection protocols that balance scientific validity with practical constraints, a skill that defines field research across disciplines. Second, they build data pipeline literacy, understanding how raw sensor voltages become calibrated measurements, get logged to databases, undergo quality control, and generate visualizations that communicate findings to non-technical audiences. Third, they develop systems thinking about coupled human environmental systems, recognizing that pollution isn't just a chemistry problem, but involves transportation patterns, industrial processes, policy decisions, and community impacts. The platform progression matters for career preparation. Students who start with microbit or Arduino, then transition to Raspberry Pi and Python data analysis, emerge with the exact technical stack that entry-level environmental tech positions require. When my students apply for summer research internships or university lab positions, the ones who can demonstrate deployed wireless sensor network to monitor urban heat island effect, collected 6 weeks of temperature data across 12 locations, analyzed spatial patterns with Python and GIS mapping, they stand out dramatically. That's not hypothetical resume building, it's the actual job description for environmental monitoring technicians and junior researchers. For students interested in climate science, ecology, or environmental policy, these kits provide earlier, more authentic exposure to career tools than almost any other educational technology. What's the learning progression from basic to advanced environmental monitoring? A well-designed progression typically spans 4 to 5 years and builds through increasing layers of complexity: sensor diversity, programming sophistication, study design independence, and statistical analysis depth. Here's the pathway I've seen work reliably for middle school through high school students. Foundation stage, ages 9 to 11, 6 to 12 months. Single parameter monitoring with pre-built kits. Students deploy a temperature logger or simple weather station, collect data for 1 to 2 weeks, create basic graphs, and identify daily patterns. Learning focus is consistent data collection, understanding what sensors measure, creating time series visualizations. Block-based programming or turnkey systems work best here. This builds the discipline and curiosity that sustains longer investigations. Expansion stage, ages 11 to 13, 12 to 18 months. multi-parameter monitoring with modular systems. Students combine temperature, humidity, and air quality sensors, design studies comparing two locations like schoolyard versus parking lot or bedroom versus kitchen, and begin asking why questions about patterns. Programming progresses to customizing data collection intervals, adding conditional logging, and exporting data for spreadsheet analysis. Introduction to calibration concepts and measurement uncertainty happens here. Integration stage, ages 13 to 15, 12 to 24 months, network deployments with text-based programming. Students deploy multiple sensor nodes, learn wireless data collection, begin using Arduino or Python to process data, and connect measurements to explanatory variables, traffic patterns affecting air quality, tree cover influencing temperature. Statistical analysis grows to include correlation, regression, and hypothesis testing. Students begin contributing to citizen science databases and comparing their data against professional monitoring stations. Specialization stage, ages 15 and up, ongoing. Student-designed investigations addressing self-selected questions. They specify sensors needed, design custom data collection systems, conduct multi-month studies, and present findings to authentic audiences. Science fairs, city council meetings, research symposiums. Programming includes database management, automated visualization, and potentially machine learning for pattern recognition. Some students begin collaborating with university researchers or environmental organizations on community monitoring projects. The key to successful progression is layering skills rather than replacing tools. The microbit they started with at 10 becomes a wireless sensor node in their 13-year-old mesh network. The Arduino they learned at 12 controls the pump in their 15-year-old water sampling robot. Each new capability builds on prior foundations rather than abandoning them, exactly how professional research skills develop, and exactly what makes these investments in environmental monitoring kits worthwhile over the long term. So here's the verdict. Environmental monitoring kits represent one of the rare educational technology categories where the learning investment compounds across years rather than hitting dead ends. Your child won't outgrow these tools. They'll deepen their sophistication with them, much like a young musician doesn't abandon their instrument but learns increasingly complex pieces. For families just beginning this journey, the Microbit Smart Citizen Kit or SparkFun Environmental Combo Board offer accessible entry points with clear upgrade paths. For students ready for industry-standard tools, the Arduino Environmental Science Bundle builds the exact skill set that university labs and environmental careers require. And for pure field science without programming overhead, the Kestrel Drop D3 delivers professional data quality that can contribute immediately to citizen science networks. The real victory isn't any single kit. It's watching your child transition from "I'm measuring temperature" to "I'm investigating how urban tree canopy affects afternoon microclimate patterns" to "I'm analyzing whether our school's air quality improvements correlate with attendance data." That progression from data collection to scientific investigation to community impact is what environmental monitoring kits make possible, and it's learning that lasts far beyond any classroom assignment. That wraps up this episode of the STEM Lab podcast. Thanks for listening. New episodes come out every Monday, Wednesday, and Friday, so you've always got something new waiting. If you've got a minute, I'd be incredibly grateful if you'd leave a 5-star rating and write a quick review. It sounds like a small thing, but it genuinely helps other parents and educators find the show when they're searching for this kind of content. And if you haven't already, hit subscribe or follow so you get notified the second a new episode drops. I'll catch you in the next one.